My name is Ramesh H.G., Assistant Professor of Mathematics, Government Posted College, Chittoor. Today I am going to explain properties of groups. So we know what are groups, what is the definition of group, some examples. And today we are going to explain properties of groups. So we know what is group. Group is an algebraic structure with binary operation star satisfying four properties: closure property, associative property, identity property, inverse property, and commutative property. Then it is called as an abelian group. Closure property means for all a comma b belongs to G, a star b belongs to G. Associative property is for all a b c belongs to G, a star b star c is equal to a star b star c. Identity property, a star e is equal to e star a is equal to a. Inverse property, for all a belongs to G, a star a inverse is equal to a inverse star a is equal to identity element. Commutative properties, a star e is equal to e star a is equal a star b is equal to b star a is equal to b star a. Then we call it as an abelian group. So several examples are there for groups. So set of all integers z is an abelian group under addition. In that set, 0 acts as identity element, minus 2 acts as inverse of 2, minus 1 acts as inverse of 1, minus 10 acts as inverse of 10, and so on. So totally it satisfies all the properties: closure, associative, identity, inverse, and commutative property. Therefore, set of all integers is a group under addition. Similarly, set of all rational numbers, set of all real numbers, set of all complex numbers, these are all groups under addition. They are all satisfying the 5 properties, and hence they are all abelian group under addition. If you come to q minus 0, that means non-zero rationals, non-zero reals, non-zero complex numbers, these are all groups under multiplication. These are all groups under multiplication, non-zero rationals. So there, 1 acts as identity element, and 1 by 2 acts as inverse of 2, 1 by 3 acts as inverse of 3, 2 by 3 acts as inverse of 3 by 2, and so on. So and hence the non-zero rationals forms an abelian group under multiplication. So you come to the properties of groups. The identity element of a group G is unique. The identity element of a group G is unique. So you consider any group, the group set of all integers. Set of all integers is a group. Set of all rationals is a group. Set of all real numbers is a group under addition. So you come to set of all integers. So here 0 acts as identity element under addition. So the element 0 only acts as identity element under addition. No other element acts as identity element under addition. That is, the identity element of a group G is unique. If you consider non-zero rational numbers, 1 acts as identity element under multiplication. No other element acts as identity element under multiplication. So this theorem states that the identity element of a group G is unique. So group consisting or contains only one identity element. Only one identity element. It does not contain 2, 3, 4 identity elements. It contains only one identity element. So in Z, 0 is the identity element under addition. In Q, 0 is the identity element under addition. In R, 0 is the identity element under addition, and 1 is the identity element under multiplication in q minus 0, non-zero rationals. So this is the property. The identity element of a group G is unique. For this proof, let us consider two elements, E and E dash are the two identity elements. Suppose a group which has two identity elements. So by the property of identity element, A star E is equal to E star A, that is equal to A. By the property of identity element, A star E is equal to E star A, that is equal to A. And E dash is also an identity element. A star E dash is same as E star A dash, that is equal to A. So here E and E dash are two identity elements of a group G. In reality, no group contains two identity elements, only contains one identity element. Suppose group has two identity elements, E and E dash, then by the property of identity element, A star is equal to E star A is equal to A. A star A dash is equal to E star A dash is equal to E star A. E star dash E star E dash star A is equal to A. Then from equation 1 and 2, A star E is equal to A star E dash. So cancel A on both sides. E is equal to E dash. Or if you multiply by A inverse on both sides, A inverse into A, then we get E is equal to E dash. And hence the identity element of a group G is unique. So this is one of the important property. The identity element of a group G is unique. So group contains only one identity element. No group contains 2, 3 identity elements. This is one property. Second property is the inverse of an element of a group G is unique. So each element in a group has its own inverse element. Suppose A is the inverse of B. A is inverse of B, you say. A is inverse of C. A is not inverse of C. A is inverse of B only. C is inverse of D only. H is inverse of K, like that. No two elements have same inverse element. For example, set of all integers, you take, it's a group under addition, set of all integers. Minus 2 is the inverse of 2. Minus 3 is the inverse of 3. Minus 4 is the inverse of 4. Minus 4 is the inverse of 4. But minus 4 does not act as inverse of 5, 6, 7, like that. It is only inverse of 4. Minus 3 is only inverse of 3. Minus 10 is only inverse of 10. So one element has one inverse. One element has one inverse. That is the property. The inverse element, the inverse of an element of a group G is unique. Suppose B and C are the inverse elements of A. So here in this group, suppose A has two inverse elements B and C. So by the property of inverse elements, A star B is equal A star B is equal to E, and A star C is equal to A star B is equal to B star A is equal to E, and A star C is equal to C star A is equal to E. So let B is equal to we can write B as B star E, because E is the identity element. B is equal to B star E. This is equal to B star A star C. A star C is identity element. So in place of E, we write A star C. Then A star B A star B star C. A star B is, or B star A is equal to identity element. So E into star C, that is equal to C, and hence B is equal to C. So the element B is equal to element C. That means if you assume that the element A has two inverse elements B and C, at last they are equal. So then B is equal to C. Therefore, inverse of an element of a group G is unique. So no two elements have same inverse elements. One has one inverse element, another has another inverse element, like that. Next one, the inverse. If A is an element of a group G, then A inverse of inverse is A. A inverse of inverse is A. That means if you take set of all integers, is a group under addition, then minus 3 is inverse of 3. Minus 3 is inverse of 3. So minus of minus 3 is inverse of minus 3. So minus of minus 3 is 3. So 3 acts as inverse of minus 3 and minus 3 acts as inverse of 3. So that is A inverse of A is equal to 3. So 3 is inverse of minus 3 and minus 3 is inverse of 3. So proof is let x equal to A inverse and x star A, because A inverse is equal to x star A is equal to A star x equal to A. So inverse of x is A. Inverse of x is A. Therefore, A is equal to A inverse of inverse. So inverse of x means A inverse of inverse, that is equal to A. So this is a very simple property of a group. Next property is if A and B are two elements of a group G, then A star B inverse. A star B inverse is equal to B inverse star A inverse. This is very important. A star B inverse is equal to B inverse star A inverse. For this you take A star B star B inverse star A inverse. You take this property. Suppose if this is equal to E, on simplification if you get E, then this acts as inverse of A star B. So if you multiply these two, we get identity element. Therefore this acts as inverse of A star B. Therefore B inverse star A inverse is equal to A star B inverse. So on simplification we get A star B star B inverse. So we take bracket to these two. Star A inverse. This is equal to A star, this is E star, this is A inverse, is equal to E. So A star E is equal to A. So A star A inverse. A star A inverse is equal to E. Therefore A star B whole inverse is equal to B inverse star A inverse. So this is one of the important property of groups. In a group G, the equations, in a group G, A star x equal to A star y, then x is equal to y. If we have A star x equal to A star y, then automatically x is equal to y. So how can you prove this one? So let A star x star A is equal to y star A, then x equal to y. So these are two equations. So first you take A star x equal to A star y, multiply by, you take x star A is equal to y star A, x star A is equal to y star A, multiply by A inverse on both sides. So A inverse, multiply A inverse on both sides. So A into A inverse is equal to E, A into A inverse is equal to E, therefore x star E is equal to y star E, and hence x equal to y. So similarly this one, first one. So this is one of the property of groups. So here also next property, in the group G, the equations A star x equal to B and y star A is equal to B as unique solutions. So if you take y star A is equal to B, multiply by A inverse on both sides, y star A inverse is equal to B star A inverse, and A star A inverse is equal to E. So y star E is equal to y, that is equal to B star A inverse. This is the solution of the given equation. Similarly, this has solution. For example, 0 is the identity element of ZQR under addition. So 0 is the only unique identity element of ZQR. I already explained. 1 is the identity element of non-zero Z. 1 is the identity element of non-zero QR under multiplication. It is not Z, it is Q, non-zero Q, non-zero R under multiplication. So if you take modular groups, so 0 acts as identity element, unique identity element, and inverse of 1 is 1. Unique inverse element is also unique. Here also Z3 under addition modulo 3, 0 acts as identity element and no other elements acts as identity element. Inverse of 1 is 2 and inverse of 2 is 1. So inverse elements also unique. If you take Z4, 0, 1, 2, 3, 4, 0 acts as identity element and inverse of 1 is 3, inverse of 2 is 2, inverse of 3 is 1. So inverse elements also unique. Z5, 0, 1, 2, 3, 4. So 0 acts as identity element, inverse of 1 is 4 and inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 1. So every element has its own unique inverse element. In similarly Z5 under multiplication, 1 acts as identity element, and inverse of 1 is 1, inverse of 2 is 3, inverse of 3 is 2, inverse of 4 is 4. So each element has its own unique inverse element. Z8 under multiplication, 1, 3, 5, 7, you take 1, 3, 5, 7 only elements, and multiplication is 1 acts as the identity element under multiplication. So inverse of 1 is 1, inverse of 3 is 3, inverse of 5 is 5, inverse of 7 is 7. So every element has its own inverse element. So identity of a group G is unique, inverse of any element is unique. So these are some properties of groups. Thank you.